Hi everyone, welcome to Charmworks one more time. If today is your birthday, then happy birthday to you. Today we'll be learning about a probability problem which is commonly referred as birthday paradox. But it isn't a paradox at all. It just seems like a paradox, but it is. So let's dive in what the problem is all about. Imagine a group of 30 people, 30 random people. Let's say we've just picked 30 people from the streets. So let's consider 30 random people, random sweet cute people from the street. So this is our number 1 guy, this is number 3, and this is number 30. How much do you think it is probable of any two people from that group having the same birthday? So we are imagining a group of 30 people, 30 random people. Let's say we pick them from streets, and now we want to know how much it is probable of any two people from that group having the same birthday. I mean, how much is the chance of at least one birthday match in? Of course, there can be several birthday match. We have no problem with that. If that happens, so then chill. That's why we're saying the term at least. Now, what our intuition suggests? So there are 365 days in a year if you don't consider leap years. So if anyone's birthday is in February 29, no offense man. Now you may ask, what if there are twins among those 30? So we also have to mention that there aren't any twins among them. Also, we're considering that every birthday is equally likely among all those 365 days. Which isn't completely true, I guess, because if you notice, people tend to marry a lot during a specific season, depending upon where on the earth you do live in, and if they can't hold their beer, if they do stuff without any shield, there will be a lot of newborn babies after 9 months for obvious reason. This is applicable also for holidays. I mean, 9 months after holidays, those days will be more likely. But for the sake of simplicity, let's say all the days of the year is equally likely to be anyone's birthday. So let's go back to our 30 people, 30 random people from the street, and let's try to understand how much it is probable of any two people among this group of having the same birthday. Now, what our intuition suggests? There are 365 days in a year. Among those 365 days, 30 people will have at most 30 days as their birthday. Now, imagine 30 days among 365 days. So, what do you think? What is your guess? What should be the probability of having any birthday match among our group? It should be very less, right? What is your guess? Maybe your guess is just 30 over 365. Or roughly, it is just 1 over 12. Or is just less than 10%. At least according to what our well-functioned brains suggest. But the reality can be often disappointing and a bit mind-boggling and counterintuitive, but it's true. One thing we'll all agree is that in this group of 30 people, what can happen? There can be a birthday match, at least a birthday match, or there can be also the case, in that case, there is no birthday match. So we can say that in this group of 30 people, there can be birthday match, or it is also possible that there isn't any birthday match. So we can say that the probability of birthday match plus probability of no birthday match should be equal to 1, because in this group of 30 people there can be a birthday match, at least a birthday match, or there can be no birthday match. To find out the probability of having at least a birthday match, first we will derive probability of no birthday match. Now you may ask why we are doing that, why we are not calculating this probability directly. And this is because finding this probability directly will be a lot harder. So to derive, what are the chances that two people share a birthday in a group of 30? So if we calculate that, if we want to calculate that directly from this probability of birthday match, we could list the pairs and count all the ways they could match. But that's hard. There could be 1, 2, 3 or even 30 matches. It's like asking what's the chance of getting one or more heads in 30 coin flips. There's so many possibilities. There can be heads on the first throw or the third or the last, or even first, second, third, even all the keys. So to calculating what's the chance of getting one or more heads in 30 coin flips won't be won't be any easier. So what can we do to easily find out the chance of getting one or more heads in 30 coin flips? Just flip it around. Rather than counting every way to get heads, find the chance of getting all tails. And that's simple. And after finding the probability of getting all tails, if we subtract that from 1, then we'll get the probability of getting one or more heads in 30 coin flips. And in that way, calculating these problems becomes a lot easier. And finding this is too easy. We know that in case of flipping a coin, the possibilities of head or tail is for every flip is equal. It is just 50%. I mean half. So for getting all tails in our 30 coin flips, we have to multiply half for 30 times. So the result will be half to the power 30. So the probability of getting one or more heads in 30 coin flips will be just simply 1 minus this answer. 9.31 into 10 to the power minus 10, which will be 99.99999%. So in that way, calculating it becomes a lot easier. So we didn't have to go to all those hassles of driving, of finding the probability of heads coming in different ways. So we just simply calculated the probability of getting all tails, because the alternate of this is the probability of what we want to calculate. Because if we don't get all the tails in 30 coin flips, that means there will be one or more heads, and that's what we want to calculate. So the same approach is in this case also. In case of calculating this directly, probability of birthday match, there are 365 days in a year. So, and there are 30 people, and 30 people can have birthday pairs in different ways. So calculating all those will be a lot harder. So what we are doing, we are calculating the probability of no birthday match. And after finding that, if we subtract that from 1, we'll easily get the probability of birthday match. In this case, we are showing the calendar of 2020. So that's a leap year. That's why here is February 29. But we are considering the case that is not leap year. So this February 29, let's say this just vanishes. To calculate the odds of no match, we should start small. Let's first take only 2 persons. Let's first take only 2 persons, any 2 persons from our group of 30 people. Let's calculate the odds that the one pair of people that we've taken have different birthdays. One day of the year will be the first person's birthday, which leaves only 364 possible birthdays for the second person. So the first person's birthday can be any day. So the first person's birthday can be any day out of all those 365 days. So it is just 365 out of 365. But when we are calculating the second person's possible birthdays, as we are considering that both birthdays must be unique. So, and already all but one birthday is accounted for the first persons. So which leaves only 364 possible days for the second persons. So the probability of different birthdays for that 2 people or any pair of people from our group is just 364 out of 365, because this is just one. And if we calculate that is just 99.7%. Which is pretty high. Now let's take one more person from our group. The probability that she or he has a unique birthday in this small group is 363 out of 365, because there are 2 birthdays already accounted for the first 2 persons that we have taken. So in case of taking any 3 people, of having no birthday match, of having just unique birthdays, that will be just 365 out of 365 for the first person, 364 out of 365 for the second person, and 363 out of 365 for the third person, and which comes to be 0.991 or 99.1%. So I guess both of this result is very convincing, as we see, because in case of 2 or 3 persons, it is not likely to have any birthday match. So there is a high probability, there is almost to a certain that there won't be any birthday match. Now consider the whole 30 people from our group, and let's calculate the probability of no birthday match among all these 30 people. So that will be, because we are taking 30 people. So already you have got the idea, you've got the sequence. So for 30 people, the probability of no birthday match will be 365 over 365 for the first person, and 364 over 365 for the second person, and 363 over 365 for the third person, and all the way to 336 over 365 for the last person, for the 30th person. So this is for the first person, this is for the second person, and this is for the last person. Because we have already said first persons can have any days as his birthday among all those 365 days, and that leaves only 364 possible birthdays for the second person, and so on. So the last person will have 336 possible birthdays, to have unique birthdays, to have no birthday match among all this group. He or she has 336 possible birthdays, because other 29 days are already accounted by the 29 person of the group. And also be aware of that, don't write this last term 335, this will be 336, as you can remember that when in case of 3 people, in case of 3 person, 365, 364, 363, this 363 is just 365 minus 3 plus 1, so that's why this is 363. Same way, the possible birthdays for the last person will be 336 minus 30 plus 1, or you just can simply just think it like 336 minus 29, because 29 days are already accounted by the other 29 person. But this form will remember because we want to generalize this as a formula. Let's first calculate what will be the probability of no birthday match of our 30 people. So the final answer will be, because there is 365 30 times, so denominator will be 365 to the power 30, and numerator will be 365, 364, 363, ... last term will be 336. Now we can try to simplify this a bit, because we just can simply write this upper portion. If we write this as 365 factorial, and then, because 365 factorial means all the way to 1, but here in the numerator we have only up to 336, not all the way to 1. So we have to balance this by taking 335 factorial in denominator, and 365 to the power 30 will be also in the denominator. So this is a form, or you can even think of it as like 365, because this we can also think as 365p30. So then just simply 365p30 over 365 to the power 30. So you can use this form or you can use this form, whatever you like. Both will produce the same answer, because we all know NPR equals to n factorial by n minus r factorial. So 365p30 will be 365 factorial over 365 minus 30 factorial, that means 335 factorial. So this portion is 365p30. So now finally we have determined the result of no birthday match in our group of 30 people, and that comes out to be 0.2936838. So there's a 29.36% chance, or almost 30% chance, that there will be no birthday match in our group of 30 people. So what will be the probability of at least a birthday match in our group of 30 people? That will be just simply, so the probability of birthday match will be 100% minus 29.36%, and that comes out to be 70.63%. So that's it, that's our answer. Now we can see there is a 70.63% chance of a birthday match and 29.36% chance of no birthday match. That can be rounded to 70, and so now it seems a bit odd that there is more chance of having a birthday match in a group of 30 people than the case of having no birthday match. So now it seems pretty odd because there are 365 days and 30 people will at most have 30 days as their birth. Now we have derived that there is a more chance of having a birthday match in this group of 30 people. Now you know what is more interesting. If we consider 50 people, then this probability of birthday match will go to 97%. All that seems pretty odd. In case of 50 people, there is more people, then that is almost certain that with 50 people, with 50 random people, there will be at least a birthday match. That is quite certain. Now 50 people is more than 30 people, so obviously it's gonna mean more likely. Now what our intuition suggests? Our intuition suggests that with 150 people, with even 150 people, it's still not even gonna be 50-50 chance. But now we're seeing that only with 50 people we have a 97% chance of having at least a birthday match. Now let's generalize the formula. So let's declare variable k. So this k will mean the amount of people, about how many people we are talking about. Our final formula, in case of k people, the probability of birthday match will be 364 into 363 ... 365 minus k plus 1. Remember, when we are talking about 30 people, the last term was 336. That was 365 minus 30 plus 1. And what will be in the denominator? Then in the denominator, it will be just simply 365 to the power k. This is just what we have derived before. We just generalized that formula. And this can also be written as, form like this form or this form. So the general formula, if you want to complete that will be 365 factorial over 365 to the power k into 365 minus k factorial. Or we can also write it as like 365p k over 365 to the power k. This is all just what we have derived earlier for 30 people. We have just generalized that case. This is the first form, and this is the second form, this is the third form. Now let's note down some of the results. So the probability of 50% or around when k is just 23 people. So that means that only a group of only 23 people, there is a 50-50 chance of having a birthday match or no match. And there is a almost around 70% chance when k is equals to 30 people, that we have derived in this case. 97% chance when k is just 50 people. 99.97% chance when k is equals to 75 people, and 99.99999% chance, or almost certain, that there will be a birthday match when k is just 100 people. That means, well, 100 is a fairly large number, but it is still way less than 365. If you notice that, if we think that 100 is, although it is a large number, it is still less than a third of 365. So normally you may guess that there should be a 30% chance of a birthday match because there is 365 days. That's what our intuition says. But now we got the result, and that is so interesting that when we have 100 people, the probability of birthday match is almost certain. So when you see a group of 100 people, there will be a birthday match. Now you may ask one thing, that in case of 100 people, the probability of a birthday match is 99.9999%. Even if we take more people, this percentage will increase. But can you say how many people is necessary to have 100% probability of birthday match? I mean, like you say, when k is equals to 120 people, this will be 99.999 and there will be more probability, but that won't be 100% in case of 150 people too. So the question is, for how many people probability will turn to exactly 100%? And the answer is when k is greater than 365. Because as we see, there are 365 days in a year, and when we have more people than the days in a year, there must be at least a birthday match. Like say, when k is 366, there are 366 people, then 2 people must have the same day as their birthday. Now the question is, why is our intuition so wrong? Why? When we first guessed, remember when we first guessed that in case of 30 people, the probability of birthday match, we guessed that will be less than 10%. But when we have calculated, we get that the result is the surprising result was 70%. So why this is like this? Why our brain could not guess 70% at the first place? Because our brain is not so great at grasping non-linear function or non-linear behavior. If we represent the number of people in this axis and the probability in this axis, how our brain interpret this probability, our brain likes to think everything's linearly. So that means what we have guessed earlier, that for 10 people, the probability should be 10 over 365 or roughly 1 over 36. And for 30 people, our guess was 30 over 360, that means 1 over 12, 30 over 365 actually, but roughly 1 over 12. So that means when the number of people become 3 times, the probability of birthday match will increase by 3 times 2 and so on. But in reality, if we take the values that we have calculated from 10, 30, 50, 75, the graph would look like something like this. So it won't be linear, it would be non-linear. That's why intuitively we can't guess this correctly. As you have seen previously, that for 23, 30, 50, 75, 100 people, how is the probability changing? 50, 70, 97, 99, 99. It is growing exponentially. And another important thing is, whenever you want to calculate this using your calculator, you can get math error because of the limit of your calculator. Don't be frustrated with that. That's just because most of our calculator calculate up to 2 digits. So whenever this turns to 3 digits, most of the calculator can't calculate. So then you have to use some online calculator or some software, not the traditional scientific calculator. So don't be frustrated with that. Just keep that in mind. Now, the next question is, what is the reason behind this high probability? To understand that, we have to understand a field of mathematics which is known as combinatorics. Combinatorics is a field of math which discusses about different combinations, like and of course we get these words from the different combinations of the previous word. Consider 3 people, how they can be connected. You can easily say that 3, only 3 connection. This we can write mathematically as 3C2 because we have 3 people and we are calculating the ways of connection between any 2 people of them. So that is mathematically known as 3C2. In this case, we can easily see that they can be connected in 3 ways. But we can also use the formula for NCR, which is the formula of combinations. So according to that, this will be just n factorial over r factorial into n minus r factorial. In this case, if we apply this formula, this will come 3 factorial over 1 factorial, 3 minus 1 factorial, 2 factorial. That means 3 factorial is 6 and 2 factorial is 2, 6 by 2, that is 3. Or we can also think it like we have three people A, B, C. Any two people of them will get AB, BA, BC, CB, CA, AC. I mean 6 patterns. But half of them are redundant because AB and BA, they both are the same thing. So that's why we have to divide it by 2. 6 by 2, that means 3. Think about 5 people, let's say. Now, how many ways they can be connected? A could have connection with B, with C, with D, with E. Then B can have connection with C, D, E. Then C can have connection with D or E. And also D can be connected with E. Now we can see how many connection in this case. 4, 3, 2, 1. 10 connections. And that is interesting. When we had 3 people, the possible connection was 3. But when we have 5 people, the possible connection jumps to 10. Notice one thing, the amount of people increases is just 2. But amount of connection increases 3 to 10 all the way plus 7. The amount of connections for 5 people, this 10 we could also derive from 5C2, which is just simply 5 factorial over 2 factorial into 5 minus 2 factorial. So that comes out to be also 10. So it is not necessary that we have to draw this diagram every time. In case of determining the amount of connections, we just have to simply use this formula of combination. Now let's say, how many pairs could be generated for 10 people? The connections, the pairs will be more, and we don't have to necessarily draw this diagram. We just simply calculate that using 10C2. So that comes out to be 45. Same goes for 15 people. It will be just simply, for 15 people it will be just 15C2, and 23 people it is just 23C2s. Same way, the case we are considering here is for 30 people. So for 30 people, the amount of connections they could be connected in 30 C2 ways, and so on. So as the number of people grows, as the number of people increases, we can see the number of pairs, the number of possible connections increases by a greater amount. So you can see that from 5 to 10 people, the people just increased by an amount of 5, but the connections is increased by huge amount. So for 23 to 30 people, the people just increased by 7, but the connections increased by in a whole lot more amount. So for 50, 70 and 100 people, you can see the amount of connections. In case of 70 people, how many ways any two of them can be connected, or any pair can be generated? That is just 2,415. If you wanna see a connection between them, just for 15 people, the amount of, here you can see the amount of people. We have written the amount of people here and the amount of pairs in here. For 15 people, it comes out to be 105. Now if you notice that what is the square of 15? 15 square is just simply 225. Okay, fine. And also for 30 people, the amount of pairs is just simply 435. So what is 30 square? 30 square is just simply 900. And for 50 people, amount of pairs just simply 1225. What is 50 square? 2500. Now notice one thing, the 105 is simply just a bit off than the half of 225. In the same way, what is half of 900? It is just simply 450. And the connections for 30 people is 435, which is also a bit off from 450. And also for 50 people, the amount of connections or the pairs that could be generated for 50 people, taking any two of them, in case of 50 people, any two of them could be connected in 1225 ways. So the total number of pairs will be 1225. And what is 50 square? It is just 2500. And what is just simply the half of 2500? That is 1250. So we can see that in all the cases, the amount of pairs, if we want to connect the pairs with the amount of people, if we say the amount of people by n, if we use the letter n for amount of people, we can say that these pairs is actually equals to n square, and we will multiply that into half. I know that it isn't totally right, because it isn't actually half, because you see that for 50 people it is just 1225, it is not 1250. But it is just all the case a bit off. I hope you get the idea that it is almost close to the, very much close to the half of the square of the amount of people. So we can say that pairs is equals to half into n square, or we can just simply say pairs, this amount of pairs is just simply varies as the amount of people square. So you can see there's a quadratic relationship. There's a quadratic relationship between the amount of people and the amount of pairs that could be generated from that number of people. Now, let me plot a graph using Desmos, and we'll plot a graph using these values, and also see how much it is off from the ideal equation that we have tried to implement these values, how much it correlates. We'll get that. Now get back to the main point. So we can see, so we have already seen the relations between the amount of people and the pairs that could be generated from those people. And now when you get the idea that the 30 people may seem a little bit less, because I have been talking for this half an hour that 30 people is way less. 30 people will have at most 30 days as their birthday, but there are 365 days, so the probability of any birthday match will be very less. That we have guessed earlier. But then we have, after doing some math, that we get surprising results that for 30 people, there's a 70% chance of having a birthday match. To get that intuitively, now it may make more intuitive sense, because 30 people may seem a lot less, but 30 people will generate 435 pairs, and all those pairs, every pair could be responsible for a birthday match. Among all these pairs, there could be a birthday match. So now we have to think in this way that there are 435 pairs and any of them could result in a birthday match. So now the 70% chance of having a birthday match doesn't seem odd at all. Whenever your brain can grasp this non-linearity, this non-linear behavior, then it doesn't seem odd at all. Now, if you've made this far, then you understand that how few people it takes to have a birthday match. Comment your birthday and let's see how many people it takes to have the first birthday match in the comment section. Right now my channel is very small with just 26 subscribers. If ever my channel gets like say millions of subscribers, just thinking about that is giving me joy. Then there will be pairs and pairs, millions of pairs of birthday matches. What an occasion that will be. So comment your birthday. Hey, you still there? Let's game up a bit more because it's been fun, I guess. Can you say how many people will it take to exactly match your specific birthday? In this case, you don't care about how many pairs of random dudes will find in the comment section. You only care about how many people will it take to exactly match your birthday. This question is a bit tricky. You can find your birthday twin in the first comment. Also, there is possibility even if thousands of people comment their birthday, your own may not match. So how can we put this in a mathematical perspective? Let's say, in this case also, the probability of you find your birthday twin plus the probability of you don't find your birthday twin will be equal to 1. And in this case also, we'll first derive what is the probability of that you don't find your birthday twin, and what will be that? Let's say in this case your birthday is just one day among all those 365 days in a year, and now all the other people, in case of that probability of you don't find your birthday twin, all the other people can have their birthdays just any days out of all 364 days, one except that is what is your birthday. So among the 365 days, one day is your birthday and all the other people will have birthdays in the other 364 days without your birthday. Doesn't matter that among those 364 days, all the other people can have birthday matches, like say 30 people can have birthday in the same day, another 60 people can have a birthday in the same day, but nobody will share your birthday in that exact day. So in this case, to find out the probability that you don't find your birthday twin, what we have to do, let's say that whoever first comment, his birthday can be any day out of all the 364 days except your birthday. And the next one, the second commenter, his birthday can be any days except your birthday. And this is also common for the other people too. Just notice one thing, here we're writing 364 by 365 all the time. We are not like say continued it in a way like 364 then 363 then 362 in that manner, because in this case we don't care about among all the other people, among all the other days, 364 days, how many pairs are generated. We just only care that nobody shares your specific birthday. So in case of that nobody shares your specific birthday, that's just one day. So other people's birthday will be any days among 364 days. So we have to continue it for like how many people we are talking about. So let's say for n people, we are talking about n people, that among those n people that you don't find the probability that you don't find your birthday twin, that will be just simply 364 out of 365 to the power n. So this will be the probability of you don't find your birthday twin. So what will be the probability that you find your birthday twin? That will be just simply that will be simply 1 minus this probability, the probability of you don't find your birthday twin, and that is 364 out of 365 to the power n. So now we write this in a mathematical context. Now let's say what is the probability that you find your birthday twin for, let's say, just 30 people. Now in this equation, if you put the values of n 30, then what will be the probability? The probability will be 0.07. That does mean that just only 7.9%. So there's just only 7.9% chance of that you find your birthday twin for 30 people. So how much will this probability for, let's say, just 300 people? For 300 people, it will be 56.1%. And what will be it for 3,000 people? For 3,000 people, it will be 99.97%. And if we increase people more and more, then this percentage will increase 99.9999, and just eventually we can say that like kind of 100%. So now you can see that to be ensured that you find your birthday twin will now require a lot of people. This is different from the earlier case. In case of earlier case that you just care about how many pairs, you just need only 70 to 100 people to be quite certain that there will be birthday match. But in case of that you want to know that you find your birthday twin, your specific birthday twin, the values of n will be more. We can also represent this formula in a different way. Like say, if you want to know that in case of probability of like say 90% or 95% that you find your birthday twin, what is the recurrent number of people? So in this case, p is a function of n, but we want to write this formula as a form that n will be a function of p. So in that case, let's say probability equals to 1 minus 364 over 365 to the power n. We can say 364 out of 365 to the power n is equals to 1 minus p. And now if we take ln in both sides, then it will be ln 364 out of 365 to the power n equals to ln 1 minus p. Now this ln 364 over 365 to the power n, we can write this as n ln 364 over 365 ln 1 minus p. So n will be ln 1 minus p by ln 364 over 365. And what is ln 364 over 365? That is just this value, minus 0.0027434 whatever. And just also remember that if we want to completely ensure that the probability that you find your birthday twin is 100%, then p is equal to 1. And in case of p is equals to 1, that means ln 1 minus 1, that means ln 0, which is undefined. So just remember one thing, that you can have the number of people required for like say 99.999999999% probability that you have your birthday twin. But in case of 100% probability, we can say that there can be millions of people, and there could be a case that nobody's birthday won't match yours. That can also happen, because we can never ensure that P will be exactly 100%, but it is more likely that if there's a millions of people, there's a 99.9999% chance of having you have your birthday twin. But there's still a bit of chance that you don't have your birthday twin. So keep that in mind, and this is just some mathematics, and you can use this form or this form, whatever, to be sure that how many people it requires to have, like say 90% chance that you have your birthday twin, or 95% chance, or 99.99% chance that you have your birthday twin. And one thing you'll notice that if you have like say 2,000 or 3,000 friends in Facebook, then you will notice that there's a high chance that one or two of your friends maybe have birthdays the same day as yours. So thank you for watching this whole video, and now let's comment your birthday and let's see how many people it takes to have the first birthday match in the comment section, and also how many people it takes to exactly match your specific birthday. Thank you. And also, if you like the video, please consider like and also consider subscribing.